morning, dear students. Today we are going to study the applications of op-amp. Already we have discussed the working of an inverting amplifier. Now next is the non-inverting amplifier. The non-inverting amplifier is the one whose output voltage is in phase with the input voltage. Now in the case of the non-inverting amplifier, the output signal voltage and the input signal voltage are in phase. When the positive half cycle of the input signal is applied, the output signal is also positive half cycle. And when we apply the negative half cycle of the input signal, the negative half cycle of the amplified output signal is obtained. Now let us observe the circuit diagram of the non-inverting amplifier. In this circuit, the input signal is applied to the non-inverting input terminal of the op-amp. The resistor Ri is connected between the inverting terminal and the ground. The feedback resistor is connected between the inverting terminal and the output terminal of the op-amp. Now in this circuit, Ii is the current flowing through the resistor Ri and If is the current flowing through the feedback resistor. Now in the case of the non-inverting amplifier, the input signal is applied to the non-inverting input terminal of the op-amp. Now the voltage across the node A is equal to the input voltage, because according to the concept of virtual ground, voltage across node A is equal to voltage across node B. Since we are applying the input signal to the non-inverting input terminal of the op-amp, voltage across the inverting terminal is also equal to the input voltage. Now the expression for the output voltage can be obtained by applying Kirchhoff's current law to the node A. According to KCL, look at the circuit diagram. II is the current entering the node, IB and IF are the currents leaving the node. So according to KCL, II is equal to IB plus IF. Now since the input impedance of the op-amp is infinity, no current can flow through the input of the op-amp. Therefore, IB is equal to 0. Now according to KCL, II equal to IB plus IF. II is the current entering into the node, IB and IF are the currents leaving the node. Therefore, II equal to IB plus IF. Since the input impedance of the op-amp is infinity, no current can flow through the input terminal of the op-amp. Therefore, IB equal to 0. Now we can write II equal to IF. Now what is II? II is the current flowing through the resistor Ri. Now one end of the resistor Ri is at virtual ground and other end of the resistor Ri is connected to the ground. Now the voltage across resistor Ri is nothing but the input voltage, because the one end of the resistor Ri is at virtual ground. Now voltage across node A is equal to the input voltage. Therefore, voltage across resistor Ri is nothing but the input voltage. Now current II is nothing but V in divided by Ri. According to Ohm's law, I equal to V by R. Therefore, current flowing through the resistor Ri is nothing but V in divided by Ri. Now what is IF? IF is the current flowing through the feedback resistor. Now one end of the feedback resistor is at virtual ground, other end of the feedback resistor is connected to the output terminal. In the case of the non-inverting amplifier, the output voltage is positive. Therefore, voltage across the feedback resistor is given by V0 divided by VA. V0 is the output voltage, VA is the voltage across the inverting terminal. Now the voltage across the feedback resistor is given by V0 minus VA. In the case of non-inverting amplifier, output voltage is positive. Therefore, voltage across feedback resistor is V0 minus VA divided by RF gives you the current flowing through the feedback resistor. Therefore, let us substitute in this equation VA divided by Ri, that is equal to VA minus V0 by RF. VA minus V0 is the voltage across feedback resistor divided by RF gives you the current flowing through the feedback resistor. Therefore, II is nothing but VA by RI and IF is nothing but VA minus V naught by RF. Since voltage across node A is equal to the input voltage, we will now substitute Vin place of VA. Therefore, the equation now becomes Vin by Ri, that is equal to Vin minus V naught divided by RF. We will now rearrange this equation. We will write the equation in terms of the voltage gain or output voltage. Now, V naught divided by RF, that is equal to, take Vi by RF term to the left hand side of the equation. V naught by RF, that is equal to Vi divided by RF plus Vi by Ri. Let us take RF as common in this equation. Equation becomes Vi by RF, that is equal plus Vi by Ri. So now, we will take Vi as common in this equation. The equation becomes V naught equal to Vi into RF by Ri, that is 1 plus RF by Ri. So that is V naught equal to Vi into 1 plus RF by Ri. Now take Vi to the left hand side of the equation. So equation becomes V naught divided by Vi, that is equal to 1 plus RF by Ri, which is the expression for the voltage gain of an inverting amplifier. Now see, Vi by Ri equal to Vi minus V naught by RF. Take Vi by RF term to the left hand side of the equation. So V naught by RF equal to Vi into by Ri plus Vi by Ri. Now take RF to the right hand side of the equation. So V naught equal to RF into Vi by RF plus Vi by Ri. Now take Vi as common in this equation. V naught equal to Vi into RF divided by RF plus RF by Ri. So that is V naught equal to Vi into 1 plus RF by Ri. Take Vi to the left hand side of the equation. It can be written as V naught by Vi, that's equal to 1 plus RF by Ri, which is the expression for voltage gain of non-inverting amplifier. So in the case of the op-amp non-inverting amplifier, the voltage gain is positive. This is because the output signal and the input signals are in phase. Hence the voltage gain of the non-inverting amplifier is given by the formula 1 plus RF divided by Ri, where RF is the feedback resistor and Ri is the input resistor. One of the application of the non-inverting amplifier is the voltage follower, or it's also called the unity gain follower. Now, the voltage follower or unity gain follower circuit can be constructed from the basic non-inverting amplifier simply by making RF is equal to 0. In the non-inverting amplifier circuit, if you reduce the feedback resistor to 0, the circuit works as what is known as voltage follower, or it's also called the unity gain follower. Since the feedback path is short circuited, the working of the circuit remains the same with or input or without input resistor Ri. It is not necessary to connect the input resistor Ri. The working of the circuit remains the same with or without the input resistor Ri. So in this circuit, the inverting terminal is directly connected to the output terminal of the op-amp. Now what is voltage follower? The voltage follower is a circuit whose output voltage is equal to the input voltage. It is an amplifier whose output voltage is equal to the input voltage. Now, we know the expression for the voltage gain of a non-inverting amplifier. It is given by the formula AF equal to 1 plus RF by Ri, or V naught by Vi equal to 1 plus RF by Ri. Now, the expression for output voltage is given by the formula V naught equal to Vi into 1 plus RF by Ri. Since we have reduced the feedback resistance to 0, let us substitute RF equal to 0. Once we substitute RF equal to 0, the equation becomes V naught equal to Vi into 1 plus 0. That is V naught equal to Vi. Hence, we can say that the output voltage of the voltage follower is equal to the input voltage. Now, the voltage gain of this amplifier can be written as V naught divided by Vi. Voltage gain is nothing but ratio of output voltage to the input voltage. Therefore, F equal to V naught divided by Vi, that's equal to 1. Hence, since the voltage gain of the amplifier is 1, it's also called unity gain follower. One of the application of this circuit is that the output voltage and the input voltage are same, but then in the case of voltage follower, the input impedance is very high and output impedance is very low. Hence, it is used for impedance matching purposes. So, in the case of voltage follower, input impedance is very high and output impedance is very low. So, it is used for the impedance matching purposes. The next is the op-amp adder or the summing amplifier. The op-amp adder or the summing amplifier is the one whose output voltage is equal to the algebraic sum of the input voltages. It's also called the summing amplifier. It can be constructed from the basic inverting amplifier by connecting number of input resistors. In the case of inverting amplifier, we apply the input voltage through a resistor Ri. Now, in this circuit, V1, V2 and V3 are the input voltages which are applied to the inverting terminal of the op-amp through the resistors R1, R2 and R3 respectively. That is, V1 is the input voltage which is applied to the inverting terminal of the op-amp through the resistor R1. And V2 is the input voltage which is applied to the inverting terminal of the op-amp through the resistor R2. V3 is the input voltage which is applied to the inverting terminal of the op-amp through the resistor R3. Now, RF is a feedback resistor which is connected between inverting terminal and the output terminal of the op-amp. Now, let us consider I1 as the current flowing through the resistor R1, I2 is the current flowing through the resistor R2, I3 is the current flowing through the resistor R3, IF is the current flowing through the feedback resistor RF. The non-inverting input terminal of the op-amp is connected to the ground. Now, the expression for the output voltage can be obtained by applying Kirchhoff's current law to the node A. Now, look at the circuit. In this circuit, I1, I2 and I3 are the currents entering into the node. IF and IB are the currents leaving the node. Therefore, we can write I1, I2, I3 are the currents entering into the node. IB and IF are the currents leaving the node. Therefore, we can write I1 plus I2 plus I3, that is equal to IF plus IB. Since the input impedance of the op-amp is infinity, no current can flow through the input of the op-amp. Therefore, we can write IB equal to 0. So, the expression becomes I1 plus I2 plus I3 equal to IF. Now, what is I1? I1 is nothing but the current flowing through the resistor R1. One end of the resistor R1 is at virtual ground, other end is connected to the input voltage. Now, the voltage across resistor R1 is given by V1 minus VA. V1 minus VA is the voltage across a resistor R1 divided by R1 gives you the current flowing through the resistor R1. It is nothing but I1. So, I1 is given by the formula V1 minus VA divided by R1. And what is I2? I2 is the current flowing through the resistor R2. It is given by the formula V2 minus VA divided by R2. Similarly, I3 can be written as V3 minus VA divided by R3. Now, I3 is the current flowing through the resistor R3. Now, look at the circuit diagram. IF is the current flowing through the feedback resistor. It can be written as VA minus V0 divided by RF. One end of the feedback resistor is at virtual ground, other end of the feedback resistor is connected to the output terminal. Therefore, VA minus V0 divided by RF is the current flowing through the feedback resistor. Let us substitute here. V1 minus VA divided by R1, which is the current flowing through the resistor R1. V2 minus VA by R2 is the current flowing through the resistor R2. V3 minus VA divided by R3 is the current flowing through the resistor R3. VA minus V0 by RF is the current flowing through the feedback resistor. Now, voltage across node A is equal to 0 in this case, because we have connected the non-inverting input terminal to the ground. So, we will now substitute VA equal to 0. Since voltage across node A is equal to 0, let us substitute VA equal to 0. Therefore, equation becomes V1 by R1 plus V2 by R2 plus V3 by R3, that is equal to minus V0 divided by RF. Therefore, V0 is given by the formula V0 equal to minus RF into V1 by R1 plus V2 by R2 plus V3 by R3. Now, in this equation, let us select all the resistors are of equal values. If R1 equal to R2 equal to R3 equal to RF equal to R, we will now select all the resistors of equal values. Then equation becomes V0 equal to minus of V1 plus V2 plus V3. Hence the output voltage of the op-amp adder is equal to negative algebraic sum of the input voltages. Hence, the circuit can be used as an op-amp adder or summing amplifier. So, it is an amplifier whose output voltage is equal to algebraic sum of the input voltages. The next is the op-amp subtractor or the difference amplifier. Op-amp subtractor or difference amplifier is the one whose output voltage is equal to algebraic difference between the input voltages. Now, let us study the circuit diagram of the op-amp subtractor or op-amp difference amplifier. Here in this circuit, V1 and V2 are the input voltages which are applied to the inverting terminal and non-inverting input terminal of the op-amp respectively. V1 is the input voltage which is applied to the inverting terminal of the op-amp through the resistor R1. What is the input voltage V2 is applied to the non-inverting input of the op-amp using the voltage divider formed by the resistors R2 and R3. RF is a feedback resistor connected between inverting terminal and the output terminal of the op-amp. Now in this circuit, voltage across resistor R3 is nothing but the input voltage which is applied to the non-inverting input of the op-amp. It can be determined using voltage divider rule. Now the voltage divider rule says that voltage across any resistor connected in series is equal to the product of the applied voltage and that resistor in which the voltage is to be determined divided by sum of the resistances in the circuit. Now voltage across node B is given by a formula V2 into R3 divided by R2 plus R3. Voltage across R3 is nothing but the input voltage applied to the non-inverting input of the op-amp. Therefore, V2 into R3 divided by R2 plus R3 is the voltage across the non-inverting input terminal. Now the expression for the output voltage can be obtained by using the superposition theorem. The superposition theorem states that in any linear bilateral network consisting of fixed sources and resistances, voltage across any specified terminal is equal to algebraic sum of the voltages caused by individual voltage sources acting alone while other sources are non-operative. In this circuit, we have applied two input signals, namely V1 and V2. In order to analyze the working of the circuit, you have to connect the individual voltage sources alone. That means you have to connect, say for example, you have to connect V1 input voltage source V1 and V2 must be connected to the ground. And then you have to determine the output voltage caused by the input voltage V1 acting alone. Next we have to determine the output voltage caused by the input voltage V2 acting alone with the input voltage source V1 connected to the ground. Now let us consider the input voltage source V1 alone is connected while the input voltage source V2 is connected to the ground. In this case, the circuit works as an inverting amplifier. Look at the circuit diagram. Let us connect the second voltage source to the ground and we are applying only the input voltage source V1. Now, in this case, non-inverting input terminal is connected to the ground. The input voltage is applied to the inverting terminal of op-amp through the resistor R1. Therefore, the circuit works as an inverting amplifier. Now the expression for the output voltage of an inverting amplifier is given by the formula VO equal to minus RF by RI into VI. Now here let us consider VO1 is the output voltage produced by the input voltage source V1 acting alone while V2 is connected to the ground. So VO1 is given by the formula VO1 equal to minus RF by RI into V1. This is the expression for output voltage produced by the input voltage source V1 acting alone while V2 is connected to the ground. Now next step is to connect the input voltage source V2 while V1 is connected to the ground. When the input voltage source V2 alone is connected, then the circuit works as a non-inverting amplifier. Now look at the circuit. V1 input voltage source V1 is connected to the ground while the input voltage V2 alone is applied to the circuit. Now the circuit works as a non-inverting amplifier. You know the expression for the voltage gain of non-inverting amplifier, it is given by the formula 1 plus RF by RI. Now the voltage across a non-inverting input terminal can be determined using the voltage divider rule. It is given by the formula V2 into R3 divided by R2 plus R3. Now the output voltage VO2, which is the output voltage caused by input voltage source V2 acting alone while V1 is connected to the ground. So with input voltage source V2 acting alone, the circuit works as a non-inverting amplifier. So the output voltage VO2, it is equal to 1 plus RF by R1, which is the voltage gain of non-inverting amplifier, into voltage across a non-inverting terminal. Let me write it as VB. Already we have determined the value VB. So VO2 equal to 1 plus RF by R1 into VB, where VB is the voltage across the non-inverting input terminal. Now the VB can be determined using voltage divider rule. VB is equal to V2 into R3 divided by R2 plus R3. It can be determined using voltage divider rule. Now VO2 is given by the formula 1 plus RF by R1 into VB. 1 plus RF by R1 is the voltage gain and VB is the voltage across the non-inverting input terminal. Now VO2 is given by the formula 1 plus RF by R1 into voltage across a non-inverting input terminal. It's nothing but VB, that is V2 into R3 divided by R2 plus R3. Now we have determined the output voltages caused by V1 acting alone. We have considered it as VO1, and then we have determined the output voltage caused by V2 acting alone. We have considered it as VO2. Now what is the output voltage, total output voltage? Total output voltage is equal to algebraic sum of the output voltage caused by individual voltage sources acting alone while other sources are non-operative according to superposition theorem. Therefore, the output voltage VO, that is equal to VO1 plus VO2, where VO1 is the output voltage produced by the input voltage source V1 acting alone, and VO2 is the output voltage produced by the input voltage source V2 acting alone. So now equation number 2 represents the output voltage caused by input voltage V2 acting alone, and VO1 is the output voltage caused by input voltage source V1 acting alone. So now let us substitute in this equation VO equal to minus RF by R1 into V1 plus 1 plus RF by R1 into V2 into R3 divided by R2 plus R3. Now in this equation, let us substitute all the resistors of equal values. Let us consider all the resistors are of equal values. Say R1 equal to R2 equal to R3 equal to RF equal to R. Then output voltage VO is equal to V2 minus V1. From this equation we can understand that the output voltage of op-amp subtractor is equal to algebraic difference between the input voltages. Hence the circuit works as the op-amp subtractor or the op-amp difference amplifier. Next, let us study the non-linear applications of op-amp. The first one, that is op-amp differentiator. The op-amp differentiator is the one whose output voltage is equal to, output voltage is proportional to the derivative of the input voltage, or we can say that output voltage is equal to negative instantaneous rate of change of input voltage. This op-amp differentiator circuit can be constructed from the basic inverting amplifier circuit. In the basic inverting amplifier circuit, if the input resistor Ri is replaced by a capacitor, the circuit is called op-amp differentiator or derivative amplifier. Now, in this circuit, the input signal Vin is applied to the inverting terminal of the op-amp through a capacitor C. And RF is a feedback resistor which is connected between inverting terminal and output terminal of the op-amp. The non-inverting input terminal of the op-amp is connected to the ground. Now, let us consider II is the current flowing through the capacitor and IF is the current flowing through the feedback resistor. Now, II is nothing but can also be written as IC, which is the current flowing through the capacitor. IF is the current flowing through the feedback resistor. Now, the expression for the output voltage can be obtained by applying Kirchhoff's current law to the node A. According to Kirchhoff's current law, II is equal to IB plus IF. II is the current entering into the node A. IB and IF are the currents leaving the node. Therefore, we can write II is equal to IB plus IF. Look at the equation. II is also equal to IC. It is the current flowing through the capacitor. So, IA can also be written as IC, that is equal to IB plus IF. Since the input impedance of the op-amp is infinity, IB is equal to 0. Therefore, we can write IA equal to IF or IC is equal to IF. Now, let us derive the expression for the current flowing through the capacitor. Now, from the basic definition of current is nothing but rate of flow of charges. That is I equal to Q divided by T. In the case of alternating current, we use the formula I equal to dQ by dt. Since in the case of alternating current, the rate of flow of charge keeps on changing with respect to time. So, we use the formula IC equal to dQ divided by dt, where Q is the charge stored on the capacitor plates. Now, Q is equal to C into Vc, where Vc is the voltage across the capacitor and C is the capacitance of the capacitor. We will now substitute in this equation. IC equal to C into Vc, that is C into dVc divided by dt, where Vc is the voltage across the capacitor. Now, let us determine the voltage across a capacitor. One end of the capacitor is connected to the input voltage, other end is at virtual ground. Now, voltage across the capacitor is given by the formula V in minus VA. One end of the capacitor is connected to the input voltage, other end is at virtual ground. So voltage across the capacitor is given by the formula V in minus VA. We will now substitute in this equation. I is equal to C into d by dt of V in minus VA, where V in minus VA is the voltage across the capacitor. Now what's the value of VA? VA is equal to 0 because node A is at virtual ground. So since the voltage across node A is equal to 0, we can write I say that's equal to C into dV in by dt. Now what is IF? IF is a current flowing through the feedback resistor. One end of the feedback resistor is at inverting terminal and other end of the feedback resistor is at the output terminal. So current flowing through feedback resistor is given by the formula VA minus V naught divided by RF gives you the current flowing through the feedback resistor. So IF is equal to VA minus V naught divided by RF. Now let us substitute in the above equation. So C into d by dt of V in minus VA divided by dt, that is equal to VA minus V naught divided by RF. Now since VA is equal to 0, we have connected the non-inverting input terminal to the ground, therefore voltage across node A is equal to 0. Let us substitute VA is equal to 0. So C into dV in divided by dt, that is equal to minus V naught divided by RF. Hence V naught is equal to minus RF into C dV in by dt. Take C to the right hand side of RF to the left hand side of the equation. So VO equal to minus RF into C dV in divided by dt. Hence the output voltage is equal to negative RFC times the differentiation of the input voltage. Hence the circuit output voltage is proportional to the derivative of the input voltage. Hence the circuit works as an op-amp differentiator or derivative amplifier. Now let's study the applications of the op-amp differentiator. The op-amp differentiator circuit is used in wave shaping circuits and it is also used in the high pass filters. In the case of the op-amp differentiator, when the input is a sine wave, then output is an inverted cosine wave. And when the input is a square wave, then output is a spike wave. And when the input of the op-amp differentiator is a triangular wave, then the output will be a square wave. These waveforms can be observed in this diagram. Input signal is a sine wave, then the output is an inverted cosine wave. When the input is a square wave, then output is a spike wave. And when the input is a triangular wave, the output is a square wave. These are the input signal and output signal waveforms of an op-amp differentiator. The next is the op-amp integrator. The op-amp integrator circuit is the one whose output voltage is proportional to the integral of the input voltage waveform. This circuit can be constructed from the basic inverting amplifier simply by replacing the feedback resistor by a capacitor CF. Here in this circuit, input signal Vin is applied to the inverting terminal of the op-amp through the resistor Ri, and C is the feedback capacitor which is connected between inverting terminal and output terminal of the op-amp. The non-inverting input terminal of the op-amp is connected to the ground. Now, current II is the current flowing through the resistor Ri. IF is the current flowing through the feedback capacitor. IB is the current entering into the op-amp. The non-inverting input terminal of the op-amp is connected to the ground. Now the expression for the output voltage can be obtained by applying Kirchhoff's current law to the node A. According to Kirchhoff's current law, IA is the current entering into the node, IB and IF are the currents leaving the node. Therefore, we can write the expression as IA equal to IB plus IF. IA is equal to IB plus IF. Since the input impedance of the op-amp is infinity, we can write IB equal to 0. Therefore, II is equal to IF. Now, IF is nothing but the current flowing through the capacitor, because we have connected a capacitor between the inverting terminal of the output terminal of the op-amp. Therefore, IF can also be written as IC, where IC is the current flowing through the capacitor, or it is nothing but the feedback current. We will now determine the expression for the current flowing through the capacitor. Now, Vin minus Va divided by Rin is the current flowing through the input resistor. One end of the resistor is connected to input voltage, other end is at virtual ground. So voltage across the input resistor is given by the formula Vin minus Va divided by Ri gives you the current flowing through the input resistor. So Vin minus Va divided by Ri is the current flowing through the input resistor. Now, the current flowing through the feedback capacitor is given by formula dq by dt is the current flowing through the capacitor. IC equal to dq by dt. Current is nothing but rate of flow of charges. In the case of alternating current, we use the formula equal to dq by dt. So therefore, Q is nothing but charge stored on the capacitor plates. Q is equal to C into Vc, where Vc is the voltage across the capacitor. So equation can be written as Cf into d by dt of Va minus V naught. But what's the value of Va? Va is equal to 0, because node A is connected to is at virtual ground. Since the non-inverting terminal is grounded, the voltage across node A is equal to 0. Therefore, we can write Va equal to 0. Let us substitute in this equation. Vin divided by Rin, that is equal to Cf into d by dt of minus V naught. Since Va equal to 0, we get the expression Cf into d by dt of minus V naught. Now the expression for the output voltage can be obtained by integrating both sides of this equation with respect to the time t. Now let us integrate both sides of the equation with respect to time t. Integral of Vin by Rin into dt, that is equal to integral of Cf into d by dt of minus V naught into dt. Now let us rearrange this equation. Now rearranging this equation, V naught equal to minus 1 by Rin into Cf integral Vin dt. From this equation, we can say that output voltage of the integrator is proportional to the integral of the input voltage waveform. Hence, the circuit works as an op-amp integrator, or a circuit which performs the mathematical integral of the input voltage waveform. The applications of op-amp integrator, it is used in wave shaping circuits. It's also used in the case of the low pass filters. In the case of the op-amp differentiator, you've seen that when sine wave is the input voltage, the output is inverted cosine wave. So in this circuit also, when the input is a sine wave, the output of the integrator will be a cosine wave. And when the input is a square wave, then the output of the op-amp integrator will be a triangular wave. These waveforms can be observed in these diagrams. When the input is a sine wave, then output will be a cosine wave. And when the input is a square wave, then output will be a triangular wave. The integration is just reverse process of differentiation. In the case of differentiator circuit, you have seen that when the input is a triangular wave, the output is a square wave. So in this case, when you apply the square wave input, then output will be a triangular wave. Yes. The next is the logarithmic amplifiers using op-amp. A logarithmic amplifier is the one whose output voltage is proportional to the natural logarithm of input voltages. The circuit can be constructed from the basic inverting amplifier circuit simply by replacing the resistor RF by a semiconductor diode. It's basically an inverting amplifier. Here the input voltage Vin is applied to the inverting terminal of the op-amp through the resistor Ri, and a semiconductor diode is connected between inverting terminal and output terminal of the op-amp. Now the non-inverting input terminal of the op-amp is connected to the ground. Consider Ia is the current entering into the node, or it is a current flowing through the resistor Ri. Ib and If are the currents flowing through the op-amp and the semiconductor diode. Now let us consider the current flowing through the semiconductor diode as Id, or it is the current flowing through the feedback path. So we will now consider this current as Id. Id is the current flowing through the semiconductor diode. Now the expression for the output voltage can be obtained by applying Kirchhoff's current law to the node A. According to Kirchhoff's current law, Ia is the current entering into the node, Id and Ib are the currents leaving the node. Therefore, now the expression for output voltage can be obtained by applying Kirchhoff's current law to the node A. Now according to Kirchhoff's current law, In is the current entering the node, Ib and If are the currents leaving the node. Since Ib is equal to 0, we can write Vin minus Va by Rin, which is the current flowing through the resistor Ri, that is equal to If, or it's also equal to the current flowing through the semiconductor diode. Since Va is equal to 0, the non-inverting input of the op-amp is connected to the ground. Therefore, we can write Va is equal to 0. Therefore, Vin divided by Rin, that is equal to the current flowing through the semiconductor diode. Now, for this particular circuit, the current flowing through the semiconductor diode is Id. Now one end of the semiconductor diode is at virtual ground, other end of the semiconductor diode is connected to the output terminal. Therefore, the voltage across the semiconductor diode is given by Va minus V0. One end of the semiconductor diode is at virtual ground, another end of the semiconductor diode is connected to the output terminal. Therefore, voltage across the semiconductor diode is given by the formula Va minus V0. We will now substitute in this equation. Vd is the voltage across semiconductor diode, it is equal to Va minus V0. Since Va is equal to 0, we can write Vd equal to minus V0. Let us consider this equation as equation number 2. According to Shockley's diode equation, the current flowing through the semiconductor diode is given by the formula Id equal to Is into e to the power Vd divided by eta Vt minus 1. Now what is Is? Is is the reverse saturation current and Vd is the voltage across the semiconductor diode. Eta is called offset, or it's also called the ideality factor, and Vt is the thermal equivalent of temperature, or it's a voltage equivalent of temperature. It's also called the thermal voltage. Now in this equation, the 1 Is into e to the power Vd divided by eta Vt minus 1, that's 1, the quantity 1 is very much smaller than this quantity. Since e to the power Vd divided by eta Vt is very much greater than 1, we can write Id equal to Is into e to the power Vd divided by eta Vt. Let us consider this equation as equation number 3. Now, according to equation number 1, Id equal to Vin by Ri. And according to equation number 2, Vd equal to minus V0. We will now substitute equation number 1 and equation number 2 in equation number 3. Now the equation becomes Vin by Rin, that is equal to Is into e to the power minus V0 divided by eta Vt. According to equation number 1, Id is equal to Vin by Rin. And according to equation number 2, Vd equal to minus V0. Therefore, Vin by Rin, that is equal to Is into e to the power minus V0 divided by eta Vt. Let us take Is to the right hand side of the equation. Equation becomes e to the power minus V0 by eta Vt, that is equal to Vin divided by Rin into Is. We will now take natural logarithm on both sides of the equation. So on taking natural logarithm on both sides, the equation becomes V naught divided by eta Vt, that is equal to log to the base e V in divided by R in into Is. Let us write the equation in terms of the output voltage. Take eta Vt to the right hand side of the equation. V naught equal to minus eta Vt log to the base e V in divided by R in into Is. Now here eta is a constant for a particular semiconductor diode, maybe the silicon or the germanium diode. Now Vt is also constant for particular temperature. Rin is a resistance, it's also constant. For particular temperature, Is is also fixed. All these are the constant, but only the variable is Vin. Hence we can understand that the output voltage of the logarithmic amplifier, it is proportional to the natural logarithm of input voltage. Hence the circuit works as a logarithmic amplifier. The output voltage is proportional to the natural logarithm of input voltage. Next is the anti-logarithmic amplifier using op-amp. An anti-logarithmic amplifier is the one whose output voltage is proportional to the natural anti-logarithm of input voltage. This circuit can be constructed from the basic inverting amplifier circuit if the input resistor Ri is replaced by a semiconductor diode. In a circuit, the input resistor Ri is replaced by a semiconductor diode. The input voltage Vin is applied to the inverting terminal of the op-amp through the semiconductor diode. And Rf is the feedback resistor which is connected between the inverting terminal and the output terminal of the op-amp. The non-inverting input terminal of the op-amp is connected to the ground. Let us consider Id is the current flowing through the semiconductor diode. If is the current flowing through the feedback resistor. And Ib is the current entering into the op-amp. The expression for the output voltage can be obtained by applying Kirchhoff's current law to the node A. According to Kirchhoff's current law, Id is the current which is entering into the node, Ib and If are the currents leaving the node. Therefore, according to KCL, Id is equal to Ib plus If. Since the input impedance of the op-amp is infinity, no current flows to the input terminal of the op-amp. Therefore, we can write Ib equal to 0. Therefore, the equation now becomes Id, that is equal to If. Id is the current flowing through the semiconductor diode. If is the current flowing through the feedback resistor. So we get the expression Id equal to If. Now, Id is the current flowing through the semiconductor diode. If is the current flowing through the feedback resistor. Now the current flowing through the feedback resistor is given by the formula Va minus V naught divided by Rf. One end of the feedback resistor is connected to the inverting terminal. Another end of the feedback resistor is at output terminal. So voltage across the feedback resistor is Va minus V naught divided by Rf gives you the current flowing through the feedback resistor. Therefore, the current flowing through the semiconductor diode is equal to minus V naught divided by Rf. From this circuit diagram, the voltage across the semiconductor diode, it is given by the formula. Look at the voltage across semiconductor diode. One end of the semiconductor diode is connected to the input voltage, other end of the semiconductor diode is at virtual ground. So voltage across semiconductor diode is given by Vin minus Va. Vin minus Va is the voltage across the semiconductor diode. Since Va is equal to 0, we can write Vd equal to Vin. Voltage across semiconductor diode is nothing but the input voltage. We will now consider this equation as equation number 2. Now, according to Shockley's diode equation, Id equal to Is into e to the power Vd divided by eta Vt minus 1, where Is is the reverse saturation current, Vd is the voltage across semiconductor diode, and eta is called the ideality factor or the offset. Vt is the thermal voltage, or it is the voltage equivalent of temperature. Now in this equation, the term 1 is very much smaller than the e to the power Vd divided by eta Vt. Therefore, we can write Id equal to Is into e to the power Vd divided by eta Vt. This is because e to the power Vd divided by eta Vt is very much greater than 1. We can neglect 1. So equation becomes Id equal to Is into e to the power Vd divided by eta Vt. Say equation number 3. Now let us substitute equations 1 and 2 in equation number 3. According to equation number 1, Id equal to minus V0 by Rf, and according to equation number 2, Vd equal to Vin. Let us substitute equation number 1 and 2 in equation number 3. The equation becomes V0 divided by Rf, that is equal to Is into e to the power Vd divided by eta Vt. Vd is nothing but Vin. Now let us rearrange this equation. It can be written as V0 equal to minus Is into Rf into e to the power of Vin divided by eta Vt. Now in this equation, Is is constant for a particular temperature, Rf is also constant, it's a feedback resistor, and eta is also constant. For particular temperature, Vt is also constant. So from this equation, we can understand that output voltage of the circuit is proportional to the natural anti-logarithm of input voltage, or it is an amplifier whose output voltage is proportional to the natural anti-logarithm of input voltage. Hence the circuit works as an anti-logarithmic amplifier. One of the application of the anti-logarithmic amplifier and the logarithmic amplifier is the multiplication of the two signals. The logarithmic amplifiers and anti-logarithmic amplifiers can be used to multiply the two signals. Let us consider this circuit diagram. Here, let us consider we have two input signals, say V1 and V2. Now V1 is the input voltage which is applied to the input of a logarithmic amplifier. Hence the output voltage of this circuit becomes VO. It is proportional to logarithm of the input voltage, that is log to the base E V1. V1 is the input voltage of this circuit. So its output voltage is proportional to log to the base E V1. Now V2 is the input voltage which is applied to a logarithmic amplifier. Therefore, the output voltage of this circuit is proportional to log to the base E V2. Now we are using an op-amp summing amplifier. The output voltage of op-amp summing amplifier is given by the formula VO equal to VO1 plus VO2. Since the output voltage of the summing amplifier is equal to sum of the input voltages, the equation becomes log to the base EV1 plus log to the base EV2, where VO1 is the output voltage of the first circuit, VO2 is the output voltage of the second circuit. You know, VO1 is proportional to log to the base EV1 and VO2 is proportional to log to the base EV2. Therefore, we can write VO3 is equal to log to the base EV1 plus log to the base EV2. Now, according to the logarithmic theory, we can write log mn is equal to log m plus log n. Let us use the same formula. Log to the base E V1 plus log to the base E V2 can be written as log to the base E V1 V2. Log to the base E mn, that is equal to log to the base E m plus log to the base E n. Let us use the same formula. So VO3 equal to log to the base E V1 V2. Now look at the last circuit, and the last circuit is an anti-logarithmic amplifier. The output of the summing amplifier is connected to an anti-logarithmic amplifier. Therefore, the equation now becomes VO equal to anti-logarithm of VO3 or anti-logarithm of log to the base e V1 V2. Anti-logarithm of log to the base e cancels, so we can write the output voltage is proportional to V1 V2. Hence, the output voltage is proportional to the product of the input voltages. Hence, the circuit can be used to multiply two input voltages. So this is the applications of the op-amp logarithmic amplifier and op-amp anti-logarithmic amplifier. The next is the active filters. Already we have studied two types of filters, the low pass filter and the high pass filters. The active filter circuit uses the active component like op-amp. The filter circuits are used to select a band of frequencies while rejecting other frequencies. The circuit which makes use of passive components such as resistors and capacitors and active components such as op-amp to select a band of frequencies is called an active filter. Basically there are two types of filters. One is the low pass filter and other one is the high pass filter. Here the circuit is called the active filter because the circuit uses the active component like op-amp along with the passive components like resistors and capacitors. Now let's study the theory of the active low pass filter. The active low pass filter allows the frequencies up to a critical frequencies and attenuates the frequencies above the cutoff frequencies. Or we can say that the low pass filter circuit allows the frequencies below cutoff frequency and blocks frequencies above the cutoff frequency. Let's study the working of first order low pass active filter. The circuit is called the first order low pass active filter because the circuit uses one section of resistor and capacitor. If the circuit uses two sections of resistors and capacitors, the circuit is called the second order filter. The first order low pass filter circuit allows the frequencies up to the critical frequency and blocks frequencies above the critical frequency. Let's study the circuit diagram of the active first order active low pass filter. Now this is the circuit diagram of the first order low pass active filter. We will now study the working of the circuit. Now here there is a combination of resistor and capacitor which is used as the basic low pass filter circuit. Now the basic low pass filter circuit is used as non-inverting input voltage to the circuit. Now the resistor Ri is the input resistor, Rf is a feedback resistor which is connected between the inverting terminal and the output terminal of the op-amp. Now, when the input signal is applied to the circuit, consider we are applying very low frequency signal. When you apply a very low frequency signal, the capacitor now acts as an open circuit for low frequency signals because the capacitive reactance is inversely proportional to the frequency. Therefore, at very low frequency, capacitor acts as an open circuit or the capacitor offers very high reactance to the low frequency signals. Therefore, the low frequency signals will be amplified by the circuit because the low frequency signals cannot be attenuated since capacitor acts as an open circuit. So all the low frequency signals are amplified by the circuit. Now as you increase the frequency, the capacitive reactance goes on decreasing. Therefore, when the input signal frequency crosses the critical frequency, the output voltage decreases. This is because at high frequency capacitor acts as a short circuit. So most of the input signal voltage is bypassed through the capacitor. So input voltage is not applied to the amplifier. Therefore, the output voltage decreases at high frequency. Now let us study the frequency response curve of the RC low pass filter or the active low pass filter. Now here, initially when you increase the frequency, that is at low frequency, the voltage gain remains constant. As you increase the frequency, the voltage gain drops off, the voltage gain gradually decreases. Now here in this graph, AV maximum is the maximum voltage gain. The frequency is corresponding to 0.707 times the maximum gain, or 1 by root 2 times the maximum gain, or is called the critical frequency. The frequencies below critical frequency will be allowed to pass through. The frequency above cutoff frequency will be blocked by the circuit. Now, if the circuit uses two sections of resistors and capacitors, the circuit is called the second order low pass filter. The frequency response of second order filter decreases at faster rate compared to the first order filter. That means the frequency response curve of the second order filter approaches the ideal low pass filter frequency response. Now let us study the circuit. Now the frequency, cutoff frequency of the active low pass filter is given by the formula Fc equal to 1 by 2 pi Rc, where R is the resistance and C is the capacitance used in the circuit. Since we are using the op-amp non-inverting amplifier, the voltage gain of the non-inverting amplifier is given by the formula AV equal to 1 plus Rf by Ri, where Rf is the feedback resistor and Ri is the input resistor. Therefore, AV is equal to 1 plus Rf by Ri. So, using these two formulae, we can calculate the critical frequency and also the voltage gain of the amplifier. The next is the active high pass filter. The high pass filter circuit allows frequencies above critical frequency and blocks frequencies below the critical frequency. In other words, you can say that the high pass filter circuit allows high frequency signal to pass through and blocks the lower frequencies. The circuit consists of RC section. Here the combination of capacitors and resistors are used. The high pass filter circuit is connected to the non-inverting input of the op-amp.